Hello friends, welcome back to Scientific Blunders, where you learn the don'ts first. So today we're going to tackle a problem that's taken from the textbook Concepts of Physics, Volume 1, published by Dr. H.C. Verma, and this is from the topic sound waves. So here's the problem. A source emitting a sound of frequency nu is placed at a large distance from an observer. The source starts moving towards the observer with a uniform acceleration a. Find the frequency heard by the observer corresponding to the wave emitted just after the source starts. So just after the source starts. Speed of sound in the medium is v. Okay. So many of you may have recognized that this is a problem based on the Doppler effect of sound, right? And just a quick recap on what the Doppler effect is. So let's say this is the ground, okay, and we have a source S that's moving with a speed Vs, which stands for speed of the source, and let's say there's an observer, our usual stickman. The observer is labeled O, and the observer is moving with a speed Vo, which stands for speed of the observer. Okay, and let's say the source is going to emit sound waves in all directions, and the wave emitted in this direction is going to travel towards the observer, and let's say the speed of the sound in the medium is v. Okay, so this is the notation we're going to use, and the Doppler effect tells us that if this is the configuration that we're looking at, so the speed and the observer, or excuse me, the source and the observer are moving in the same direction, in this particular configuration, the Doppler effect tells us that the frequency that the observer is going to hear, so I'm going to call this the frequency observed, is going to equal nu, which is the frequency of the source, times v minus v0 or vo divided by v minus vs. Okay, so v is the speed of the sound in the medium, vo is the speed of the observer, and vs is the speed of the source. Okay, so this is the standard formula for the Doppler effect. So can we use this expression, this very standard expression, to solve this problem? Well, let's go ahead and attempt it. So what we do know is that the source starts moving towards the observer with a uniform acceleration a, correct? And we want to find the frequency just after the source starts. So if the source is moving with uniform acceleration, we can apply the equations of motion, the standard 3 equations of motion, to the source, right? So we do know that v would equal u plus at, s equals ut plus half at squared, right? I'm just writing out the standard equations of motion. V squared equals u squared plus 2as. So all three of these are valid to the source because the source is moving with a uniform acceleration. Now, just after the source starts, let's say the source starts at t equal to 0. So let's define t equal to 0 to be the time when the source starts. Okay, let me change color a little bit just to break the monotony. So let's say t equal to 0 is the time at which the source starts, right? So what is the speed of the source at t equal to 0? Well, the source starts moving, right? That's what the problem says. So that means u equals 0, correct? Right? And we want to find the frequency heard by the observer just after the source starts. So basically when the speed of the source is 0, correct? And the observer, we have not been told anything about the observer, so the observer can be assumed to be stationary, right? So at t equal to 0, okay, and I'm going to write these equations at t equal to 0, v0 is going to be 0, right? The observer is stationary, and vs is also going to be 0 because the source has just started moving, and it's going to move with uniform acceleration, but it's starting from rest. So just after the source starts, its speed is going to be 0, correct? So it's nu times v divided by v. So nu observed is just equal to the frequency of the source. Well, something seems fishy, right? Because the problem has the acceleration and it has the speed of sound in the medium, but somehow these things seem to get cancelled out. So is our solution correct, or are we missing something important? Well, I encourage you to pause the video here and think about this, and think about how the Doppler effect, how this equation was actually derived. So assuming you have paused the video and are back, let's, whenever I'm stuck in a situation like this, I try to think about the conditions under which the formula was derived. And the best thing to do is to start from first principles again and not assume any equations, but just start from the absolute basics. Okay, so let's do that. Let me scroll down a little bit more to get some space. So what do we know here actually? Let's redraw the diagram. We have a source S and an observer O, correct? And the source is going to emit sound waves that travel at a speed v with respect to the medium, and the frequency at which the source emits these waves is nu. Okay, the initial speed of the source is 0, that is true, and the source starts accelerating with an acceleration a in this direction. Okay, this is all we know. Okay, so let's start from the absolute basics. Okay, so I'm going to set up a table here to record the times at which the source emits these waves and the times at which the observer receives these waves, and let's see using that whether we can find anything useful. So these are going to be the times, sorry, I meant to write these are the times at which the source is going to emit the waves, and these are the times at which the observer is going to receive these waves. Okay, so let's say the source emits the very first wave at t equal to 0. Okay, this is the first wave that the source emits, and let's also assume another variable that is not part of the problem, and that is the distance between the source and the observer initially. Okay, so let's assume that's d. So the very first wave emitted by the source is at t equal to 0, and this wave, when is this going to reach the observer? Well, it's going to take a time. This wave is going to travel at the speed v, correct, and hence it's going to reach the observer at a time d over v, correct. Awesome. So far I don't think we just use the basic definitions of speed and distance, and so very basic stuff so far. So I think this is correct. Now let's say the second wave is going to be emitted at a t that's equal to the time period. Okay, and we know that just by definition the time period is going to be 1 over the frequency, correct. And so nu is the variable given to us in the problem, but just for simplicity let's use t, and in the end we can make this substitution to recover the original data. Okay, so t equals t, or t equals capital T is the time at which the second wave was emitted, and when is this wave going to reach the observer? This wave is going to reach, now we have to be careful because we are assuming that the source starts at t equal to 0, correct, and that's when it emitted the first wave, but by the time it emits the second wave it's actually going to have traveled some distance, right? And so where is the source going to be? Let me use a different color. Where is the source going to be when it emits the second wave? Well, it's probably going to be somewhere here. Okay, let me draw this using a dotted line, or let me actually just draw it over it's probably going to be somewhere here, correct? When it's emitting the second wave, it's going to be somewhere here. And how far would it have traveled in that time? Well, this is where the equations of motion come handy, right? Because we know it started with a speed of 0, okay? So u is 0, all of these are 0. So it would have traveled distance s, which is equal to half a t squared, correct? That is how far it would have traveled. So in the time t, which is typically very short because the sound waves are emitted at pretty high frequencies, right? So it is going to have traveled a distance half a t squared in that short period of time. And so now for the second wave to reach the observer, it doesn't have to travel this entire distance d, but it only has to travel this remaining distance, which is d minus half a t squared, correct? To reach here. And so this is going to reach at a time, so it started at t equal to t, and then it's going to take how long to reach? Well, that's just the distance divided by the speed, okay? And this is the time at which, oh, I think I meant to write 1 here. So this is the time at which the first wave was received, and this is going to be the time at which the second wave is going to be received, right? And now we actually understand what they mean by corresponding to the wave emitted just after the source starts, okay? So essentially there's the wave that's emitted, just immediately at the start, and this is the one that's emitted right after that, okay? So just based on these two waves, the frequency that the observer is going to perceive is going to be based on the time difference between these waves, right? So frequency is nothing but how frequently you hear something, and so that's just 1 over the difference in the times, correct? So what is the delta t between these two waves? So the delta t is nothing but so d over v is going to cancel, so we are just left with nothing but t minus half a t squared over v, okay? And now we can make the substitution t equals 1 over nu, because t was not part of the problem but nu was. So let's make that substitution. 1 over nu minus half a by v nu squared, right? And so we can simplify this a little bit to obtain the answer in a form that is needed. So this is 1 over nu times 1 minus a by 2v nu, and so this is 2v nu minus a by 2v nu squared, and this is the difference in times at which this is the time between the observer receiving the first wave and the second wave. And so the frequency that the observer is going to observe, okay, so the frequency observed is just 1 over delta t, right? That's the definition of frequency, and so that's just going to be 2v nu squared by 2v nu minus a, right? And this is the answer, right? So now this is great. Okay, we learned something new, right? We started off by using the standard expression for the Doppler effect, and we got an answer of nu. And now we started from first principles and we got an answer 2v nu squared divided by 2v nu minus a. So what exactly went wrong? This standard expression for Doppler effect applies to almost all of the standard problems, right? Why did it not work all of a sudden? Well, the reason it didn't work is that this expression for the observed frequency was derived under the assumption that the source and the observer are moving with constant velocities, right? So constant speed in a constant direction. Whereas all of a sudden when that assumption changed, right? We were told that the source is actually accelerating. So this formula is no longer true because the assumptions under which it were derived are no longer valid. And so starting from first principles, we get a different expression that involves the acceleration. So the key lesson to be learned is that, I think this deserves to be boxed. The key lesson to be learned is that this expression, this very standard, very commonly applied expression for Doppler effect, only holds true when the velocities of the source and observer are constant. So if there is any acceleration of any form, this no longer holds true. And so that, my friends, is the key takeaway of this video. And before I finish, I just have one question for you. So remember, the problem asked us to find the frequency heard by the observer corresponding to the wave emitted just after the source starts, right? So it's not just at any time, but at a very particular time, so just after the source starts. And that is what we did, right? And my question for you before we finish for today is, how is the frequency going to change? So what if you consider the third wave that the source emits and the third wave that the observer receives, and then find the frequency using the difference between 2 and 3. So is that going to be the same? Or is the frequency going to increase with time or decrease with time? And so with that, I will see you in the next video. Bye.